This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is instrument loading effects. Our objective is to take a look at instrument loading effects and examine how the act of measuring an electrical quantity can influence a circuit's behavior. Let me begin this lecture with an admission of guilt. I am guilty of not so much as lying to you, but rather I am guilty of withholding information from you. Understand I operate under the Kung Fu principle, and that I am always entitled to withhold one move from you, lest you at a later date come back to challenge me. Never forget this. Additionally, my withholding of information is essential to progressive development as a technician. If I was to present you with the true extent of reality as it is currently understood right up front, we would go nowhere. There are many deep rabbit holes down which we might dive to find more and more accurate and increasingly complex depictions of reality, truly horrifying in their complexity. Progress dictates, however, we make simplifications and necessitates we use simple models. The comforting news is this: the simple models work. For our level of detail, we really don't care about things that only minutely affect reality. If an application of Ohm's law demonstrates we should expect 120 milliamperes and an actual ammeter reads 119.4 milliamperes, I'm overjoyed I even came close, and I'm cool with a small error. A difference of 0.6 milliamperes isn't something to lose sleep about. Ohm's law is true to a reasonable degree of accuracy. Additionally, Ohm's law, as I've presented to you, acts as a linear relationship, and that any increase in voltage results in a proportional increase in current. If, however, we employed astronomically high or infinitesimally small voltage or resistance values, this simple linear relationship might break down. This being said, who cares? We don't normally deal with astronomically high or infinitesimally small values. Normally, we operate equipment as intended and leave these theoretical boundary regions to those bespectacled nerds in pure science disciplines. If you've been watching the DC circuit analysis playlist in its intended sequence, we've now arrived at a topically relevant junction that I can reveal additional details behind some of the simplifications I've repeatedly employed during the course of this series. Let's discuss instrumentation first. You've heard me say time and time again that ideal ammeters are modeled as having 0 ohms of resistance and ideal voltmeters are modeled as having infinite resistance. The truth is they don't. The truth about the truth is, who cares? In comparison to typical load elements, ammeters have extremely low resistance. Voltmeters, in contrast, have extremely high resistance. Ideally, a low resistance ammeter, when placed in series with a component is intended to measure current through, won't unnecessarily present additional opposition to a source. Similarly, ideally a high-resistance voltmeter placed in parallel with a component is intended to measure voltage across, won't present too much of a leakage path and draw additional current. Quality ammeters and voltmeters do affect circuit properties, but they don't affect it that much. Poorly made equipment, however, affects circuit properties, and sometimes these effects are noticeable. The other piece of pertinent information I've been withholding is this: voltage sources themselves aren't ideal elements either. Oftentimes, sources include a small internal resistance in series that can affect the observed electrical properties of the circuit under inspection. Long story short, there are more elements in a simple circuit than you may initially suspect, and given your new understanding of series parallel circuit analysis, we can now account for some of these less than ideal behaviors. As a basis of comparison for this exercise, consider an ideal 24-volt source and a 200 ohm resistor. In a perfect world, the resistor would experience the full 24-volt drop. And an application of Ohm's law would demonstrate that current through this system will be 120 milliamperes. As a result, this resistor would dissipate roughly 2.9 watts of power. Let's start by taking a look at non-ideal sources. Consider a non-ideal 24-volt source with, let's say, 2 ohms of resistance in series. This, by the way, is a purposeful exaggeration of what you might actually observe. It's a significant magnitude, and its effects will not go unnoticed. In the open circuit condition, or unloaded condition, no current flows through the internal resistance, and no voltage will be dropped across it. A voltmeter measuring the unloaded voltage would measure 24 volts. When a 200 ohm load is connected to the non-ideal source, current flows through the load and the internal resistance in a series relationship. The source, in effect, sees the series combination of the internal resistance and the 200 ohm load for a total resistance of 202 ohms. An application of Ohm's law demonstrates current through this system will be 118.8 milliamperes. As a result, another application of Ohm's law demonstrates the 200 ohm resistor will experience only a roughly 23.8 volt drop. As a result, the load resistor dissipates roughly 2.8 watts of power. You will note in comparison to the ideal scenario, both observed voltage and current are less than our ideal calculations would suggest. By including the small internal resistance inside a non-ideal voltage source, we account for the minor drop in voltage from the unloaded to the loaded condition you may have observed in lab. Additionally, we accounted for inefficiencies in the source, where any power consumed by the internal resistance might be directed towards losses. All these differences aside, is there really any cause for concern, even with this level of exaggerated internal resistance? Not really. There is a difference, but it's not that much. Let's now include a non-ideal ammeter in our circuit. An ideal ammeter has 0 ohms of internal resistance and does not present an additional opposition to the source. This non-ideal ammeter, however, happens to present an additional 2 ohms of resistance. The source sees the series combination of the internal resistance, the non-ideal ammeter, and the 200 ohm load for a total resistance of 204 ohms. An application of Ohm's law demonstrates current through the system will be roughly 117.6 milliamperes. Another application of Ohm's law demonstrates that V1 will be 23.5 volts. As a result, R1 consumes 2.8 watts of power. You will again note in comparison to the ideal scenario, observed voltage across and current through and power dissipated by the load resistor are less than our ideal calculations initially suggested. This being said, it's really not that bad. Let's now include a non-ideal voltmeter in our circuit that happens to present 20 kiloohms of resistance in parallel to R1. An ideal voltmeter presents infinite resistance and will not be a leakage path for current. This non-ideal voltmeter, however, happens to present a path in parallel to R1 with 20 kiloohms of resistance. The parallel combination of the non-ideal voltmeter and R1 presents a combined resistance of 198 ohms. Let's call this simplification R single prime. Simplification R single prime is in series with the internal resistance of the source and the non-ideal ammeter. An application of the voltage divider rule demonstrates that V single prime is 23.5 volts. Given R single prime is a parallel combination of R1 and the voltmeter, it can be said V1 and the voltage across the voltmeter equals V single prime, which equals 23.5 volts. Voltage across elements in parallel is the same. An application of Ohm's law demonstrates I1 is 117.6 milliamperes. Another application of Ohm's law demonstrates a leakage path of 1.2 milliamperes travels through the voltmeter. An application of Kirchhoff's current law to the series parallel circuit demonstrates that current through the ammeter is I1 plus current through the voltmeter. As a result, the ammeter reads 118.8 milliamperes, although in fact R1 experiences only 117.6 milliamperes. This is to suggest that the ammeter isn't really reading the actual current traveling through the load resistor, since its reading is artificially inflated by the leakage current through the voltmeter. Long story short, when taken in combination, these non-ideal effects result in an electrical load actually experiencing slightly different voltage and current values than the ideal scenarios suggest and as your meters would read. This is to suggest that everything is a little bit more complicated than it seems. When you take into account every little tiny detail, each new tiny detail brings with it a level of previously unseen complexity. Let's test your understanding of this concept with 2 simple examples that will get complicated rather quickly. First, the easy task. Consider a pure series circuit consisting of a 36 volt source, an R1 a 120 ohm resistor, and R2 a 600 ohm resistor. Additionally, consider a pure parallel circuit consisting of a 16 volt source, an R1 a 480 ohm resistor, and R2 a 240 ohm resistor. As a preliminary exercise, see if you can determine the voltage across and the current through each element in the system, as well as source current. These ideal values will form the basis of comparison for a follow-up exercise discussing instrument loading effects. By all means, pause the lecture and try this by yourself. If you're tracking, you should have obtained the following values. Presented without comment, you should have observed the following properties for the series circuit. I source, I1, and I2 all equal 50 milliamperes. V1 equals 6 volts, and V2 equals the remaining 30 volts. Similarly, you should observe the following properties in the parallel circuit. Both V1 and V2 equals 16 volts. I1 equals 33.3 milliamperes, I2 equals 66.7 milliamperes, and find the I source equals 100 milliamperes. If you didn't get these values, get out of here and revisit the preceding lectures detailing pure series and pure parallel DC circuit properties. Let's use these idealized values as a basic comparison for instrument loading effects and non-ideal sources. Go ahead and copy these values down for later use. Let's model the series circuit as follows. Let's say the source has 2 ohms of internal resistance, as does a non-ideal ammeter. We'll additionally make use of 2 voltmeters, each with 20 kiloohms of resistance, in parallel to R1 and in parallel to R2. You will note that in accounting for these non-ideal elements, we are no longer dealing with a pure series nor a pure parallel circuit, but rather a much more complicated series parallel circuit. As an exercise to the viewer, I invite you to determine the voltage across and the current through each resistor in this system, as well as source current. This will be a lot harder than previously. Again, we're only looking for V1, V2, I1, I2, and source current for each system. By all means, pause the lecture and try this by yourself. If you're tracking, you should have obtained the following values. The parallel combination of R1 and the non-ideal voltmeter 1 presents a resistance of approximately 119.3 ohms. Similarly, the parallel combination of R2 and non-ideal voltmeter 2 presents a resistance of roughly 582.5 ohms. The internal resistance, the ammeter, R single prime and R double prime are perfectly in series with one another. An application of the voltage divider rule to the pure series simplification demonstrates the voltage across the ammeter is 102 millivolts. An application of Ohm's law demonstrates the ammeter experiences 51 milliamperes. Ostensibly, this is the source current for this system. Another application of the voltage divider rule demonstrates that V single prime is 6.1 volts. Another application of the voltage divider rule demonstrates that V double prime is the remaining 29.7 volts. Voltage across elements in parallel is the same. V single prime equals V1, which equals V voltmeter 1, and they all equal 6.1 volts. An application of Ohm's law demonstrates that I1 is 50.7 milliamperes, and another application of Ohm's law demonstrates 304.2 microamperes is routed around I1 through the non-ideal voltmeter. Again, voltage across elements in parallel is the same. V double prime equals V2, which equals the voltage across the non-ideal voltmeter 2. They all equal 29.7 volts. An application of Ohm's law demonstrates that I2 is 49.5 milliamperes, and another application of Ohm's law demonstrates that 1.5 milliamperes is routed around R2 through the non-ideal voltmeter 2. Ultimately, accounting for these non-ideal effects, the ammeter measuring source current displays 51 milliamperes. However, because of the leakage paths presented by voltmeter 1 and 2, R1 experiences only 50.7 milliamperes, and R2 experiences 49.5 milliamperes. Voltmeter 1 reads 6.1 volts, and voltmeter 2 reads 29.7 volts. When we compare these results with our initial idealized calculations, there's a small but noticeable difference. An observer ignorant of non-ideal sources and instrument loading effects may suspect minor violation of fundamental series properties. However, a savvy aspiring technician, such as yourself, is keenly aware of the more complicated series parallel circuit underlying reality and can account for and explain these differences. Let's now take a look at the non-ideal parallel circuit. If you recall, the original circuit was a 16-volt source in parallel with a 480 ohm resistor and a 240 ohm resistor. Let's include 2 ohms of internal resistance in the source, a non-ideal ammeter used to measure source current, which happens to have an internal resistance of 2 ohms, another non-ideal ammeter used to measure current through resistor 1 that also happens to have an internal resistance of 2 ohms, and finally, the third non-ideal ammeter used to measure current through resistor 2 that also happens to have an internal resistance of 2 ohms. Finally, we include a non-ideal voltmeter that happens to have an internal resistance of 20 kiloohms in parallel with R2. As an exercise to the viewer, I invite you to determine the voltage across and the current through each resistor in this system, as well as source current. This will be much more difficult because it takes several levels of simplification to bring it down to a pure series circuit. Stay organized. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. Here's how I solve for these values. The series combination of the non-ideal ammeter and R1 presents a resistance of 485 ohms, a simplification I'm calling R single prime. The parallel combination of R2 and the non-ideal voltmeter presents a resistance of roughly 237.2 ohms. Let's call this simplification R double prime. The series combination of R double prime and the non-ideal ammeter used to measure current through resistor 2 presents a resistance of roughly 242.2 ohms. Let's call this simplification R triple prime. Finally, the parallel combination of R single prime and R triple prime presents a resistance of roughly 161.5 ohms. Let's call this simplification R quadruple prime. R quadruple prime is perfectly in series with a non-ideal ammeter used to measure source current and the internal resistance. Using the pure series simplification, an application of the voltage divider rule demonstrates the voltage across the ammeter used to measure source current is 193.3 millivolts. An application of Ohm's law demonstrates the ammeter used to measure source current experiences 96.7 milliamperes. Ostensibly, this is the source current for the system. Another application of Ohm's law demonstrates that V quadruple prime is 15.6 volts. R triple prime is the parallel combination of R single prime and R triple prime. Voltage across elements in parallel is the same. V quadruple prime equals V single prime, which equals V triple prime, and they all equal 15.6 volts. An application of Ohm's law demonstrates that I single prime is 32.2 milliamperes. I single prime is a series combination of non-ideal ammeter 1 and R1. Current through elements in series is the same. I single prime equals I ammeter 1, which equals I1, and they all equal 32.2 milliamperes. An application of Ohm's law demonstrates that V1 equals 15.5 volts. Now let's examine the parallel path on the right. An application of Ohm's law demonstrates that I triple prime is 64.5 milliamperes. R triple prime is the series combination of the non-ideal ammeter used to measure current through R2 and R double prime. Current through elements in series is the same. I triple prime equals I ammeter 2, which equals I double prime, and they all equal 64.5 milliamperes. An application of Ohm's law demonstrates that V double prime is equal to 15.3 volts. R double prime is a parallel combination of R2 and the non-ideal voltmeter. Voltage across elements in parallel is the same. V double prime equals V2, which equals the voltage across the voltmeter, and they all equal 15.3 volts. An application of Ohm's law demonstrates that I2 is 63.7 milliamperes. Yet another application of Ohm's law demonstrates 764.5 microamps leaks around resistor R2 through the non-ideal voltmeter. Ultimately, accounting for these non-ideal effects, the ammeter measuring source current displays 96.7 milliamperes. The ammeter measuring I1 displays 32.2 milliamperes, and the ammeter measuring I2 displays 64.5 milliamperes. This being said, because of the leakage path presented by the voltmeter, R2 in reality experiences only 63.7 milliamperes. Similarly, the voltmeter measuring voltage across R2 reads 15.3 volts. However, R1 really experiences 15.5 volts. As previously, when we compare these results with our initial idealized calculations, there's a small but noticeable difference. An observer ignorant of non-ideal sources and instrument loading effects may suspect minor violations of fundamental parallel properties. However, a savvy aspiring technician, such as yourself, is keenly aware of these more complicated series parallel circuit underlying reality and can account for and explain these differences. As these example problems were intended to illustrate, accounting for the non-ideal nature of sources and instrumentation, one might expect to witness small variations between calculations and real-world observations. This being said, even for such inflated non-ideal effects, the variances aren't all that bad. On a more devious level, this discussion on instrumentation loading effects served as an excellent means of tricking you into more practice and exposure with series parallel circuit analysis. If you perform these analyses correctly, especially that last circuit, you'll most likely do just fine. If not, don't worry, there will be a lot more opportunities for practice in the very near future. In conclusion, this lecture took an introductory look at instrument loading effects and discussed how the act of measuring an electrical quantity can influence the circuit's behavior. You will be overjoyed to realize that a well-constructed ammeter or voltmeter will not unduly or excessively influence the circuit's behavior, and any effects can be considered negligible for our purposes. This discussion, however, presented us with the opportunity to employ our series parallel circuit analysis skills on increasingly complex circuits. You should have an appreciation for the complexity behind the simplifications employed in circuit analysis, and you should be able to account for minute differences observed in the course of study using previously acquired circuit analysis skills. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.